Before move to the next topic, let's consider for the complex exponential function. This one is basis function for Laplace transforms. In the Fourier transform, we take the basis function of j omega. It has a real and imaginary part, but basically this one is a sinusoidal function. Let's consider only the real part of this one. Then, as over time, is a cosine omega t. So this one is looks like this one. Okay. Real parts are given like that, okay, as time goes on. But what about in the complex exponential function? Okay, s time, okay, st. Okay, let's look at this one. Complex exponential of this one, and this can be expressed by e to the sigma t times e to the j omega t. It includes these terms. It's the same as this one. So it's a gain factor is changing over time, sigma t, but basically it's a sinusoidal one. So let's consider the real part of this one. Then if sigma equals to 0, then the same as this one, you know that sigma equals to 0, then in this case it's just e to the j omega t. So the real part is cosine omega t. It's the same as this one. Okay. The next, consider for sigma is negative. Then e to the sigma t times e to the j omega t. But at this moment, sigma is negative one. So this one is a decaying over time. Okay, decaying that way. That's the e to the sigma t in this case. If sigma is negative, as time goes on, it's decreasing. But this one is alternating. By taking the real, it's a cosine. So it looks like this one. So decreasing. Okay. Last one is consider for sigma is positive. Then it will give e to the sigma t times e to the j omega t. This one shows that the alternating the sinusoidal one, this one is increasing signal pattern. So it is increasing in that way. As time goes on, it's increasing. So real terms increasing like that. So I compare the three conditions. Sigma equals to 0, it's the same as a Fourier transform. It's just a steady state, like an amplitude doesn't changing over time. But if sigma is negative, then this part is decaying. So over time, its amplitude is decreasing. But if sigma is positive, that is increasing over time. It's diverging like that. So this is the complex exponential. Let's compare that one here. In case of sigma equals to 0, it's just the same as a sinusoidal one. That shows here the blue one. Blue one is a real and imaginary part plotted in the same domains. As time goes on, this one is a time domain, but the real and imaginary part are changing like that. Real part is cosine, but the imaginary part, this one is a real and imaginary part. The y-axis is a imaginary part. This axis is real, but this one is time. So over time, I plotted the real part and imaginary part of the complex exponential. So blue one follows this curve. Okay, it's the helical style, but the helical size doesn't change. It's a steady state. That is the amplitude doesn't change over time. But if sigma is positive, that's this case, green one. Just quite similar to the blue one, but the helical size is increasing over time. Okay, that's this one. But if sigma is a negative one, that's the orange color. That helical shrinking over time. Okay, So that is the basis function for the Laplace transform. Now consider for the region of convergence of Laplace transform. Before that, we know that in the Fourier transform, d of dt, time derivative can be replaced by j omega in the Fourier transform domain. Quite similarly, due to this the property, in the Laplace transform, it's replaced by s. Okay, time derivative can be replaced by this value. Okay, this one is s. Okay, here shows a typical linear system, and system can be expressed by the differential equation. It should be starting from the 0 and starting from 0 to the m. Yt is output, xt is the input, so system can be expressed in this way. Here is a system, then xt is the input, and yt is the output. So input and output are related usually in the differential equations. From here, by taking the Laplace transform, you know that taking the Fourier transform, differentiation replaced by j omega, but in the Laplace transform we can using s. So a k is n cases. This is an, and nth derivative is s to the n, and if k equals to 1, then a1, and one derivative, that is s, and the 0 means there is no derivative. Okay, so this is Laplace transform of left hand side. Similarly, right hand side can be expressed in this way in the Laplace transform domain. The system can be defined by the ratio of output to the input. So hs is defined by ys over xs. Okay, this one can be given in this way. So summation of an and sn is denominator, but bm sm is a numerator. So it can be expressed in this way. And in mth polynomial has a m number of m zeros exist. You can mth polynomial has a m root. By factorizing, you can rewrite this one in this way. Similarly, denominator can also be factorized in this way because it's nth polynomial. It has n root. Okay, the root of the numerator is called 0. This is called numerator. Root of the numerator is called 0. The root of the denominator is called pole. So at this moment, you need to know the meaning of a pole. What is the poles? The root of the numerator, denominator. Root of denominator is called pole. And 0 is the root of the numerator. Okay. From now on, I would like to use pole and 0 terms. You need to understand what's the meaning of the pole and zeros. Okay, so pole is root of the denominator. The 0 is a root of numerator. So here is an example. xt is a right-sided signals. Okay, like that. So signal exists after t equal 0. Okay, positive times. By taking the Laplace transform, we know that the exponential function can be transformed in this way. In this case, you know that e to the minus alpha t times ut, right hand side signal has a Laplace transform is 1 over alpha plus s plus alpha. Okay, so at this moment alpha is 1 and this one is 2t. Okay, so at this moment alpha is 2, so it gives in this way. At here we need to define the region of convergence. Region of convergence for the e to the minus at, you know that region of convergence sigma is actually real part of S. In the right side signal, it should be larger than minus A, alpha, minus alpha. This is condition for the right side signals of the region of convergence. So for e to the minus t, so in this case the region of convergence is a sigma should be greater than minus 1. And for the second exponential e to the minus 2t, the region of convergence should be satisfy these conditions. But xt should satisfy both of the region of convergence. One required greater than minus 2, the other one is greater than minus 1. So we need to, and the condition is required. Both of the signals should satisfy. Because of that, the final region of convergence should be defined in this way. So this is the region of convergence for the xt. And by factorizing, it gives s plus 1 times s plus 2 will give 2s plus 3, and you can factorize this one. Then the poles of this one is minus 1 and minus 2 is poles. As we defined, root of numerator is pole. So it has 2 poles, and the 0 is minus 1.5. It's called 0. Okay, numerator root is called 0, and the denominator roots are called pole. So it has 2 poles, minus 1, minus 2, and 1 0 at the minus 1.5. So here shows that the pole and zeros. In the S domain, pole minus 1 and minus 2 are expressed here. Pole marked by the X, and the 0 is marked by the label like this one, O. So minus 2, minus 1 is a pole, minus 1.5 is 0. Region of convergence defined by the pole. So in the right side signal, the maximum pole determine the region of convergence like this way. So region of convergence is the right side of the this maximum pole. So let's consider the right side signals. Right side signal means that the time goes to the positive directions. So if xt is right sided, then the maximum root at this moment, minus 2 and minus 1, maximum root determine the region of convergence. At this moment is minus 1. That is defined as sigma r. So region of convergence should be given like that. So in this case it's the minus 1, so greater than minus 1. So region of convergence S consists of a strip of parallel to the j omega. That means this parallel line. The j omega axis is this one. When we take the Fourier transform, we use this axis. But the region of convergence is parallel to the j omega axis, and no poles. You know that no poles exist in the region of convergence. It means there is no poles in this side. So only poles exist in that side. Region of convergence cannot contain any poles. Here it means that if region of convergence include the j omega axis included exist inside of the region of convergence, Fourier transform are existing. So at this moment, j omega is included in the region of convergence, so Fourier transform also exists. And what about the left side signals? It's the same signal, but in this times it's the left side signals. By taking the Laplace transform, it will give the same expression for the previous one. But at this moment, the region of convergence is different. The region of convergence at here, to satisfy this one, region of convergence should be less than minus 1. So left sided signal, the condition are given left side, and this convergence should have satisfied sigma should be less than minus 2. Okay, xt to converging st, both sides should be simultaneously satisfied. Because of that, the end condition will give, it should be less than -2 is the final region of convergence for the XS. Okay, both of these two conditions should satisfy to converging this signal. Okay, xt to converging this integration, both conditions should satisfy. That's why it gives this one. So it has the pole location is the same and the 0 is the same. So -2 is leftmost pole, -1 is the rightmost pole, and 1.5 is 0. So region of convergence at this moment is the left side of this one. Okay, so xt is the left side signal, and sigma L is the minimum value of a pole at this moment is -2. So region of convergence should be given in this way. The same to the right hand sided one. In the region of convergence, there should be no poles. In the region of convergence, there should be no poles. Okay, and also region of convergence boundary is parallel to j omega. It means that it's a parallel. Okay, we talk about the left-sided and the right-sided signal. In the left-sided signal, region of convergence is the right side of this makes the rightmost pole. Okay, region of convergence is given as right-sided. If a left-sided signal, the leftmost pole, left side of the leftmost pole. So this is the region of convergence for the right-sided and the left-sided one. But what about the two-sided signals? Here shows the two-sided signals. Xt is defined. One is the right-sided, the other one is the left-sided. Okay, if there is a both two-sided signal cases, how are we going to handle that one? Let's take the Fourier transforms. Right-sided one taking integration 0 to the positive infinity that way, and the left side should taking -infinity to the 0. That's the left-sided signals, and the Laplace transform are given that way, but taking the infinity value are entered here. To converge this one, the sigma at the for the right-sided signal, sigma should be larger than -2 to converge in this one. Okay, by entering t goes to infinity, then sigma is greater than -2, then infinite value goes to 0. By taking the 0 value, it gives a 1 over s plus 2. That's this part. The second one, we take the integration -infinity to 0, so we enter the -infinity to time. To converge this one, the sigma should be left-sided, -1. The sigma is less than -1. Okay, then infinite value will 0, and enter the 0, then it goes to 1, so it will give a -1 over s. Okay, this is this part. So region of convergence for the right-sided are given this way, left-sided are given like that, but both conditions should be satisfied. So that is plotted over here. Here is some missing, that there should not zeros over here. Okay, see here that if I replace the okay, by factorize this one, I can write this one over like this way. I did s plus 1. Okay. I would like to factorize that one. S plus 2 times s plus 1. Common denominator, make it that. Then this one goes to the numerator, s plus 1 minus s minus 2, s plus 2. Then it will give -1 over and s plus 1, s plus 2. This means that there is no zeros exist, so this is wrong things. So this is typo. There is no zeros. There is only -1 and -2. Two poles exist, And the region of convergence, you can consider these two requirements. Then the region of convergence should be less than -1 and greater than -2. So right side of the -2 and the left side of the -1. So the overlapped region is this one. That is the region of convergence for the signal xt. So in two-sided cases, it looks like a strip one. And also there is no poles exist in the region of convergence. Till now we talk about the right-sided signal, or left-sided one, or both-sided, two-sided one. In all those signals, t goes to the 0 to the infinity is right side. Minus infinity to 0 is left side. If it defined over minus infinity to infinity, it is called two-sided one. In these signals, infinity are included. But what about the finite duration signals? If signal is finite duration and absolute integral over the limited time, then region of convergence is the entire S-plane. It means the T1, both the T1 and T2 are not infinity. It is a finite durations. Okay, finite duration means a finite time. Only signal is the finite duration of time, and I assume that the T2 is greater than T1, and take the integration, and the integrated value is finite. Then region of convergence is the entire S-plane. Okay, here shows that the Laplace transform of xt. Xt is defined over t1 to the t2, so we need to take the integration only these regions. But this inequality always satisfied if you're taking absolute value of xt and magnitude of xt. You know that magnitude of this one is equals to e to the minus sigma t. Because of e to the j omega t, by taking absolute value, it's 1. Because it's a cosine plus j omega sine, so the magnitude is a square root of cosine square plus sine square. So by definition it's 1. So this one remained here. By taking the absolute value of this one, this inequality is satisfied that way. By taking the integration, this one satisfies that one. Okay. By taking integration is less than at the T2 or T1 are given here. By taking this should be T2. Then the integration result can be interpreted in this way. If a sigma is positive, the smaller time is a larger one. So this is maximum value. But what if sigma is negative? The larger time is a larger. Okay, so this is larger number. Both of this one is finite value. Okay, we assume this one is finite, and this one is also finite. So this value, it should be finite. So that's the integrable. So in what kind of sigma can be taken, whatever the sigma can be taken. So the entire S-plane can be region of convergence in this case. Okay.